Welcome. My name is Klose, and I'm speaking to you from Berlin. Today I'm going to talk about precise Laplace asymptotics for the generalized parabolic Anderson model, which is joint work with Peter Fritz. Now, the two natural questions that you probably ask yourselves are, what actually is it, and why do we want to do it? So here you go. Think of a family x epsilon of random variables that map into a Banach space and assume that they are satisfying a large deviation principle. We are interested in so-called Laplace-type functionals, J, where we assume that the function f that maps from the Banach space x into R is sufficiently nice. I'm going to say what that means in our context later on. The goal is to obtain a precise asymptotic formula that I printed here, where the capital N is going to be related to the differentiability properties of f. For those of you who know large deviation theory, you can already see that the large deviation factor appears at the front here. That is no coincidence, and I'm going to explain why that is later on. Precise Laplace asymptotics are, for example, applied at semi-classical limits in physics. Imagine you're studying quantum mechanics, more precisely this Schrödinger type operator, where U is a potential, and you're interested in the ground state energy. That is the bottom of the spectrum of that operator. In semi-classical limits, you want to send Planck's constant to 0, which is equivalent in our context to sending lambda to infinity, and recover what you know from classical physics. Precise Laplace asymptotics enable you to do just that. Another important application are so-called heat kernel asymptotics, where you assume that x is, for example, the solution to a stochastic differential equation and has a density P that varies in time. What you want to do is you want to study that density as t is small and expand in powers of t. A first important step in order to obtain such an expansion is actually to expand the Fourier transform of that density. That's precisely where Laplace asymptotics come handy. They enable you to do it. There are many more steps that you need to do in order to obtain the claimed expansion, but precise Laplace asymptotics are a very important first step. So let me say something about previous works. For stochastic differential equations where x is just path space, Robert Azencott and Gérard Benarous in their respective 82 and 88 works have really shaped the subject. As far as classical stochastic PDEs are concerned, meaning that you have a well-defined notion of solution, Rovira and Tyndall in their 2000 and 2001 works have made important contributions. Since then, stochastic analysis has gone a long way. Namely, there was the advent of rough path theory by Terry Lyons, which has enabled people to study more irregular driving noises in stochastic differential equations that have then become known as rough differential equations, where x is just rough path space. In this context, Aida, Inahama, and later Inahama and Kawabe have contributed enormously. Now, what we want to do is we want to take the natural next step, where RDEs basically come from considering SDEs with more irregular driving noises. We want to do the same with stochastic PDEs. So we get singular stochastic PDEs, where I explain what singular means later on. Let me just say that our prime example is a renormalized solution to the generalized parabolic Anderson model, where I should say that our methods are generalizable to cover a large class of stochastic PDEs. So what is the generalized parabolic Anderson model? It's a nonlinear stochastic partial differential equation, where on the left-hand side you have the heat operator, and on the right-hand side you have a nonlinearity, so G is sufficiently smooth, and you have a driving noise, which is independent of time, which is called spacewide noise. That is a centered Gaussian random field with formal covariance structure given by the Dirac delta, and Cameron-Martin space just being the L2 on the two-dimensional torus. Also, note that there is a small parameter epsilon that modulates the intensity of the driving noise psi. Now, why is there a problem with that equation? Well, if you consider psi on a Holder-Bessow scale, then you can see that almost surely it has regularity -1 minus kappa for any kappa bigger than 0. In turn, by Schauder estimates, that means that the solution U epsilon gains 2 in regularity, which is also true of G of U epsilon, because G is sufficiently smooth. So that means it has regularity 1 minus kappa. But then, if you add up these two exponents, you get minus 2 kappa, which is just about negative, rendering the product on the right-hand side of the equation ill-defined. So there's even a problem as to define what it means to solve the equation. And this is where high-res regularity structures come in. In our context, it says the following. So the problem was that the driving noise was too irregular. So you smoothen it out by convolving it with a modifier, and then you send the smoothing parameter delta to 0. However, you're not going to converge to a limit unless you subtract an appropriate so-called renormalization counter term. That enables you to actually get a well-defined limit, U hat epsilon, in that space calligraphic xt, in probability, where t is small. So the upshot is we do have a well-defined notion of solution, and we're going to call the solution map phi. And we can further study what we wanted to study, namely Laplace type functionals. Now, if you remember the first slide, I had assumed that the random variables, in our case U hat epsilon, satisfy a large deviation principle. And that was proved by Martin Heire and Hendrik Weber in 2015. And the rate function is going to be called J. In large deviation theory, there's an important theorem called Varidance Lemma. It says the following. So assume, and that's our first hypothesis, that f is actually continuous and bounded. Then we can calculate the limit on the left-hand side here, where I emphasize this logarithm appearing, and it is precisely minus the infimum of f plus the rate function. Equivalently, that can be stated as minus the infimum of this calligraphic f over the Cameron-Martin space H, where calligraphic f is just f composed with the solution map plus Schilder's rate function. So this is the L2 norm here. And here comes our second assumption, namely that that infimum is uniquely attained. And we're going to call the minimizer H. So informally, what does Varidance Lemma tell us? So imagine that epsilon is small, so we forget about the limit. We divide by epsilon squared, and we take the exponential. Then what we see is that we have the asymptotics given here. So basically, J behaves like the large deviation factor. However, there's a problem with that, and that's precisely owed to the scale. So we can actually smuggle in exponentially big factors that we don't see in that limit here, because we take the logarithm, we multiply by epsilon squared, so this guy just becomes epsilon, and we don't see it in the limit. That means that these asymptotics are far from being precise. What we can do much better, and that is the content of our main result. So assume we have some order of differentiability for G, fix any t positive, and assume that our function f is nice, which means that it satisfies the following 4 hypotheses. So the first 2 we have already encountered. F is continuous and bounded, and calligraphic f has a unique minimizer. And we need certain differentiability that is formulated in hypothesis 3. So f is Cn plus 3 in the Fréchet sense, near when you plug the minimizer into the solution map, phi of h. Further, we need to assume that the minimizer is non-degenerate, meaning that the Hessian of f is actually positive. That means positive as in the sense of quadratic forms. Then we do have the precise asymptotic formula that I printed here, where we recover the large deviation factor. But we do have explicit constants that rule out the appearance of exponentially big terms that we've seen on the last slide. Now, there is a technicality that I have swept under the rug, namely that if we fix any t bigger than 0, then we need to assume that the explosion time of U hat epsilon is actually bigger than t, so that we have a well-defined expression. Unfortunately, I don't have time to go into the steps of proof. So let me just say as much. The vicinity of the minimizer contributes the bulk of the integral already in classical Laplace asymptotics. So first step is the localization procedure, followed by the application of the Cameron-Martin theorem. That gives us a functional which we want to tailor expand in the noise intensity epsilon, along with precise estimates of the terms and the remainder. That's the most important thing. And then we analyze the terms in that expansion. And then we use our hypothesis H2 to eliminate the linear term in that expansion. And precisely by H4, the non-degeneracy of the minimizer, we get exponential integrability of the quadratic term that ensures in turn that A0 and then also A1 and AN are actually finite. And with that, I thank you for watching. I'm looking forward to the discussion, where I'm happy to go into details of